I hope you're having a good day, and thank you for studying math with me. Today's topic is factoring polynomials. The first and last thing you do whenever you're factoring is check to make sure if you can factor out the greatest common factor. And so the first example is this one. You see that in each term there's a factor of 6a squared, so we can factor that out, and that's the complete factorization. So the greatest common factor was 6a squared. In a slightly more complicated example, we have this one. We can observe that there is a 7x squared y squared in each term, and so it can be factored out thus, and that's factoring out the greatest common factor. That's our example 1. Example 2 is having a polynomial that looks like this. In this case, not only is there a common factor of 2 throughout, but there's also a common factor of x minus 2 in each term. Consequently, we can factor 2x minus 2 out, and we're left with this expression. Sometimes we do a technique called factoring by grouping, and usually what happens is there's 4 or more terms involved when we do factoring by grouping. So here we can see we have 4 terms, and if we slice them up, grouping the first 2 together with a single underscore and the last 2 together with a double underscored, we have done some grouping, and we can factor a common factor of r squared out of the first one and minus 5 out of the second 2. And so what happens is we're left with an s plus 3, which is a common factor, which we in turn factor out, and there's the final answer, r squared minus 5 times s plus 3. Here again, we have 4 terms. We're going to group the first 2 together and factor out an m squared. We're going to group the last 2 together and factor out a common factor of n. And so doing, there's our grouping, and here's our factoring the m squared out of the first 2, the n out of the second 2, and you notice now there is a common factor of 4 minus n, which can be factored out, and the final answer is this one. Another example, we have this. We can observe that there's a common factor of 3y squared in the first 2 terms. There's a common factor of 2 in the second 2 terms. So let's group those together this way. Single underscore and double underscored. We will factor out the numbers that or the variables that I said, 3y squared from the first pair and 2 from the second. And you observe that there's a common factor of 3y minus 5 in the remaining, and that means the final answer is this. Similarly, we can factor a trinomial, meaning there are 3 terms. This is 5z squared is the first term, 4z is the second, and minus 12 is the third. It does say if possible, because sometimes you can't factor these, and if you can't, you call them prime. So here's a process. You can guess and check, but I propose doing something perhaps different, so you're not looking up to the sky and guessing. This process says you take the coefficient of the first term times the constant coefficient, and that's going to be minus 60. We try to come up with numbers that will multiply together to give minus 60, but we'll add together to give 4. And certainly minus 6 and plus 10 will do the trick. Then we rewrite the trinomial as a four-nomial, splitting up the middle term of 4z into 10z minus 6z. Now we have 4 terms which can be group factored. We single underscore the first 2, we double underscore the second. Out of the first 2 we factor out a 5z. Out of the last 2 we factor out a minus 6. In each case, what we're left with is a common factor of z plus 2, so the answer to this problem can be written thus. Let's look at another example of the same kind of type problem. So again, we will multiply the 12 times the minus 3, and that will give us a negative 36. And we want to find numbers that will multiply together to give negative 36. At the same time, will give us minus 5 as a middle term. Minus 9 and plus 4 fill the bill. I rewrite the trinomial as a four-nomial, breaking the middle term into the sum of those two. Then out of the first two, I will factor a 4t. Out of the last two, I will factor a minus 3. What emerges is a common factor of 3t plus 1, and that means that common factor can be factored out, and we have factored that trinomial thus. Here is the next example. If we take 3 times 16, we will get a positive 48. But when we look at all the possibilities where you can multiply numbers together to get 48, these are all of them, we realize that none can add to 15. That means there's no way we can achieve this factorization. That means we will declare this trinomial to be prime. That means it can't be factored anymore. Sometimes you combine processes. Here, the problem is made easier by factoring out a common factor, and it looks like 3 is a common factor. So if we factor 3 out first, we're left with 8x squared plus 14x plus 5, which can in turn be factored. We multiply 8 times 5 to get plus 40, and we realize that the middle term can be decomposed into plus 4 and plus 10. So we go through the group factoring process, and we realize we can factor a 4x out of the first two, single underscored. We can factor a 5 out of the second, double underscored, and then we have the complete factorization, which is this. You cannot drop the 3 because we're talking about doing a complete factorization of the problem. There is, or are, I should say, identities. Here's the example. Whenever we have a plus or minus b whole squared, that's going to be a squared plus or minus 2ab plus b squared. If we recognize that, that allows us to factor something like this, because we will realize that the first term is 7x whole squared, the last term is 2y whole squared, and if we check, we find that the middle term conforms to that. That means the factorization of this is 7x plus 2y squared. You will get the same answer if you work through it the other way, but sometimes it is quicker to recognize a pattern. Likewise, we have this problem. We realize that the first term is 9ab whole squared, the last term is 5 squared, and we check, is this twice the product of those terms? And it is, so this can be factored into 9ab minus 5 whole squared. Another common identity is the difference of perfect squares. This is a binomial, and we know from earlier that a squared minus b squared is a plus b times a minus b. So if we look at this binomial, we recognize that this is going to be 8r whole squared minus 7 squared, which means it can be factored this way. Similarly, 13u cubed squared, and the other one is 12v squared squared. So this is also a difference of perfect squares, and it can be factored into a minus b times a plus b. The role of a is being played by 13u cubed. The role of b is being played by 12v squared. And here we have a situation where the first term is 2c minus 3d. The second term is 4f whole squared, so it can be factored thus. And in this one, it is useful to combine, again, some processes that we have. If we look carefully at this, we see that this first 3 terms is x plus 9 whole squared. Again, we're using this identity. So what we have is x plus 9 whole squared minus 25 squared. That is x plus 9 whole squared minus 5y whole squared. And that can be factored this using this identity. In this one, if we recognize that these last three terms, if I factor a minus out, that is y plus 5 whole squared. So that means this expression is same as 2x whole squared minus y plus 5 whole squared. And then this can in turn be factored this way. 2x minus y plus 5 and 2x plus y plus 5. Again, using the same identity. There's also identities, and there are two of them, for factoring differences and sums of perfect cubes. So a cubed plus or minus b cubed is a plus or minus b times a squared minus or plus ab plus b squared. There is a difference in the SIGNs of these two. One mistake students often make is thinking this should be a 2. It's not. It is just AB. So again, we will recognize that if we're confronted with t cubed plus 1,000, we want to recognize that 1,000 is 10 cubed, and that means that this can be factored as the identity above with the plus sign. Similarly, here we recognize that 8s cubed is 2s whole cubed. That means that this can be factored as the difference of perfect cubes, and again you see that the signs alternate, and this is 2s whole squared. Sometimes it can be a little bit more disguised. Here I recognize that this is 5u cubed whole cubed, and this is 6 v to the 4th whole cubed. So I make that observation. Then this is the difference of perfect cubes, which can be factored in this way. 6 times 5 is 30. It's going to be a plus because of the minus in the middle. And this is 36v to the 8th, which is the square of 6v to the 4th. Sometimes you do a topic concept, I guess, called U substitution. This is used often in calculus. If I observe this factoring problem, I realize that I have something being squared plus something to the first power plus something to the 0 power. That means, or motivates, a substitution of saying, let's let u equal 3x plus 1. Then, if I substitute everywhere I see 3x plus 1, u, I will have 8u squared plus 10u minus 25. This trinomial I can factor. If I take the product of 8 times minus 25, I get minus 200. And I'm seeking something that I can multiply together to give minus 200 and plus 10. Plus 20 and minus 10 do the trick. I change the trinomial into a four-nomial. Break up the middle term in the following way. I'll factor a 4u out of the first pair. I will factor a 5 out of the second pair, and I'll be left with a 2u plus 5 common factor, which I in turn will factor out. Then we will substitute back in the u being 3x plus 1. And in this case, I am going to do a little bit of simplification. And if I do the algebra, I end up with this expression. Here you see another situation where you have something being cubed minus 27, but 27 is known to be a perfect cube. It is 3 cubed. So we're going to use the identity that we talked about earlier. We're going to let u equal 3x plus 1. This becomes u cubed minus 3 cubed, which factors thus. I will substitute back in, and I will simplify a bit, and eventually get this as an answer. Also, now on this one I see that it is m to the 4th, m squared, and m to the 0. So each time it drops by a factor of 2, that motivates the substitution u equals m squared. So if I replace everywhere I have m squared with u, I get this. And so when I take 15 times minus 6, I get negative 90. I'm seeking numbers that will multiply together to give negative 90, such that their sum is minus u. I get this. So that tells me how to break up the middle term. I will do group factoring, and ultimately getting a common factor of 3u minus 2. That means it factors this way, and then I will reverse my substitution, putting the m squared in for u, and I see that this factors in this this way. So that's the way it is with factoring. Remember, time is precious. Each day must count. Do the math. It will make you strong.